or shaft work. It's good to remember this, that we can call it mechanical work though, because sometimes there's no shaft, as in the case of a piston. So this is needed for actually getting the stuff in and out of the reactor. This is produced from agitation, compression, turbines, things like that. So flow work, this is the PV work we're familiar with from Thermo 1. So we can restate the work quantity, the entire quantity is the following. Just remind yourselves, you may have heard of this as generically called PV work, depending on who taught you thermal class. This is summing overall species. So all I've done here is I've taken the work term and I've broken it out into the PV work and the shaft work. The quantity, this is the PV work that's coming in, PV work that's coming out. Now the next step is where things get important, because what I'm going to do, if you noticed here, I've got a summation with all these FIs, and here I have now a summation with FIs, and I'm going to combine those. So I'm going to wind up with an E plus PV term in the next equation I write. So now we'll combine okay, so now I have this term coming in, flow rate times E plus PV. That's the total work and energy flow in. And then the same quantities flowing out. So the total energy we can break into three components: internal energy, kinetic energy, and potential energy. In this version of Fogler, there may or may not be this term that says other. This could be like nuclear rest energy if you're going to solve the Schrodinger equation. I don't care because it'll all cancel out. But I want to be consistent. And so these are all terms we're familiar with. So I have my internal energy, my potential energy, kinetic energy, if you think about it, if your reactor were vertical, you may actually need to consider a large change in potential energy if we're going to go through this. Now, what we're going to do, so this is for each species, and remember we're subtracting the in and out terms. So what's going to happen in reacting flow systems that are common everywhere in chemical industry is that we're basically going to assume that the in and out quantities of all of this cancel out. So we're just going to neglect changes in the potential kinetic and other term. They're still there, but we're going to say that for a reactor, the changes are small enough to be negligible. And we'll do this always universally for all problems in this class, so you can forget about it. If you wanted to convince yourself of this, you could compute a quantity from some problem you've seen before, a change in kinetic energy due to a change in the velocity, and compare that to the change in energy, the enthalpy of reaction, and you'll see there's a large scale in separation. So this is a good assumption, and it makes our life a lot easier. Also, what that's going to do is leave us with a term that's U plus PV. So as a reminder, what is this quantity? U plus PV? That's exactly right. So this is where, all of a sudden, by combining the flow work and the energy work, we have HI. So I'm not going to do all the... What we're going to arrive at is equation 11.9. And that's sort of the starting point for a lot of this discussion. We're not there yet, but at least we can understand how we could get there.